There is a world that circles the Sun just inward from our own, following an orbit so nearly circular that it varies by less than 1.5 million kilometers from its nearest to its farthest point. This world completes its journey around our star in 224.7 Earth days, tracing a path that brings it closer to our planet than any other world in the solar system. At its nearest approach, it passes within approximately 24 million miles of Earth, though most of the time the distance between us stretches much farther, sometimes extending to 162 million miles when both worlds find themselves on opposite sides of the Sun. This is Venus, the second planet from the Sun, a world that has captivated human attention for as long as we have watched the sky. It appears to us as a brilliant point of light, brighter than any star, brighter than any planet, exceeded in brilliance only by the Sun and Moon themselves. Ancient observers called it the morning star when it appeared before dawn, and the evening star when it lingered after sunset, not initially realizing that these were the same celestial body viewed at different points in its orbit. The Romans named it Venus, after their goddess of love and beauty, while the Greeks called it Aphrodite. Every culture that has watched the heavens has noticed this bright wanderer and given it significance in their cosmology and mythology. From our vantage point on Earth, Venus never strays far from the Sun in our sky. Because its orbit lies between Earth and the Sun, we always see Venus relatively close to our star, either in the hours following sunset or in the hours before sunrise. This proximity to the Sun in our sky means Venus moves through phases much like our Moon, growing from a thin crescent to a full disk and back again, though these changes occur over a much longer period. When Galileo Galilei first observed these phases through his telescope in 1610, he found compelling evidence that Venus orbits the Sun rather than Earth, a discovery that fundamentally altered our understanding of our place in the cosmos. The complete cycle of phases, from new to full and back to new, takes 584 days, a period known as the synodic period, which represents the time between successive closest approaches of Venus and Earth. The orbit of Venus is remarkable for its circularity. Of all the planets in our solar system, Venus follows the most nearly circular path around the Sun, with an eccentricity of just 0.00677. This means that the difference between its closest approach to the Sun and its farthest distance is minimal, contributing to an orbital stability that has persisted for billions of years. Venus orbits at an average distance of 108 million kilometers from the Sun, or 0.72 astronomical units, where 1 astronomical unit represents the average distance between Earth and the Sun. At this distance, sunlight takes approximately 6 minutes to travel from the Sun's surface to Venus, bathing the planet in solar radiation that never varies significantly due to the orbit's near-perfect circularity. The relationship between Venus and Earth creates an interesting mathematical pattern in the sky. Venus completes 13 orbits around the Sun in almost exactly the same time it takes Earth to complete 8 orbits. This near-perfect resonance means that every 8 Earth years, Venus returns to approximately the same position in our sky relative to Earth and the Sun, creating a pattern that ancient astronomers recognized and tracked. When you plot the positions where Venus and Earth come closest together over multiple conjunctions, the pattern traces a 5-petaled flower or pentagram in space, with the points separated by 144 degrees around the circle. This geometric beauty emerges naturally from the orbital mechanics of the two planets, a quiet testament to the mathematical precision governing planetary motion. Understanding these distances and relationships requires us to appreciate the scale of the solar system. When we say Venus is 24 million miles away at its closest approach, we are describing a distance that light itself takes approximately 2 minutes to cross. Radio signals sent from Earth to a spacecraft orbiting Venus must travel across this vast emptiness, and the delay in communication becomes a significant factor in mission planning. Yet compared to the distances to other planets, Venus is remarkably close. Mars, often considered Earth's neighbor, never comes closer than about 36 million miles and is typically much farther away. Jupiter, Saturn, and the outer planets exist at distances that make Venus seem almost adjacent to Earth by comparison. This proximity has made Venus a target for exploration since the dawn of the space age. The Soviet Union's Venera program sent numerous probes to Venus beginning in the early 1960s, achieving the first successful landing on another planet when Venera 7 transmitted data from the surface in December 1970. The United States followed with the Mariner missions, using flybys to gather data about Venus's atmosphere and surface conditions. Later missions included the Pioneer Venus Orbiter and probes in 1978, and NASA's Magellan spacecraft in the early 1990s, which used radar to map the surface with unprecedented detail. The European Space Agency's Venus Express orbited the planet from 2006 to 2014, studying the atmosphere's complex dynamics. More recently, Japan's Akatsuki spacecraft has been observing Venus since entering orbit in 2015, providing continuous monitoring of the planet's atmospheric circulation patterns. These missions have revealed a world that shares many physical characteristics with Earth while diverging dramatically in its current state. The similarities begin with size. Venus has a mean radius of 6,051.8 kilometers compared to Earth's mean radius of 6,371 kilometers. This makes Venus approximately 95% the size of Earth in radius. The diameter of Venus measures 12,103.6 kilometers at its equator, falling short of Earth's equatorial diameter by only 638.4 kilometers. When we look at Venus and Earth side by side, the difference in size is barely noticeable, with Venus appearing slightly smaller but essentially the same scale. This similarity in size extends to mass as well. Venus contains 4.87 times 10 to the 24th power kilograms of matter, which represents 81.5% of Earth's mass. Given how close these values are, it should come as no surprise that the two planets also share similar densities. Venus has an average density of 5.24 grams per cubic centimeter, while Earth's average density stands at 5.52 grams per cubic centimeter. These comparable densities suggest similar internal compositions, with both planets likely possessing iron-rich cores surrounded by rocky mantles and thin crustal layers. The bulk composition of Venus probably resembles Earth's quite closely, consisting primarily of iron, oxygen, silicon, magnesium, and other elements that condensed from the solar nebula during the formation of the terrestrial planets 4.6 billion years ago. The surface gravity on Venus provides another point of similarity. Due to Venus's mass and radius, an object at the surface experiences approximately 90% of the gravitational acceleration it would feel on Earth's surface. A person who weighs 100 kilograms on Earth would weigh about 90 kilograms on Venus, a difference that would be noticeable but not dramatic. This comparable surface gravity contributes to Venus's ability to retain a dense atmosphere, as the gravitational pull is sufficient to hold even lighter gases close to the surface over geological timescales. The internal structure of Venus likely mirrors Earth's in its basic arrangement. Scientists believe Venus possesses a metallic core, probably composed primarily of iron and nickel, with a radius estimated at around 3,000 kilometers. Surrounding this core lies a rocky mantle extending up to within about 30 to 50 kilometers of the surface, where the crust begins. Unlike Earth, however, Venus appears to lack active plate tectonics. Earth's crust is broken into several large plates that move slowly across the underlying mantle, driven by convection currents in the hot rock below. This plate motion creates most of Earth's mountain ranges, oceanic trenches, and volcanic activity at plate boundaries. Venus, by contrast, seems to have a single, continuous crustal plate that behaves differently under the influence of the mantle's heat. Why these two similar planets developed such different tectonic regimes remains a subject of scientific investigation. One hypothesis suggests that Venus's crust may be too rigid or too thin to break into the large plates we see on Earth. Another possibility involves water, which on Earth acts as a lubricant that helps rock flow more easily in the crust and upper mantle. Venus's extreme dryness might make its crust less able to deform and break in the ways necessary for plate tectonics. Instead, Venus may periodically resurface itself through massive volcanic episodes, a cyclical process quite different from Earth's continuous crustal recycling through subduction and seafloor spreading. The question of why Venus and Earth, formed from similar materials at similar times in similar parts of the solar nebula, evolved such different surface conditions has fascinated planetary scientists for decades. The answer appears to involve Venus's slightly closer proximity to the Sun and the resulting differences in how water vapor behaved in each planet's early atmosphere. This brings us to one of Venus's most striking characteristics, its extraordinarily dense and hot atmosphere. Standing on the surface of Venus, if one could somehow survive the conditions, the atmospheric pressure would be crushing. The pressure at Venus's mean surface level measures 93 bars, or 9.3 megapascals. To understand what this means, consider that 1 bar approximates the atmospheric pressure at sea level on Earth. 93 bars equals the water pressure you would experience at a depth of approximately 900 meters beneath Earth's oceans. This is the pressure that would exist inside a submarine descending almost 1 kilometer below the surface of the sea, where the weight of the water column above creates forces sufficient to crush unprotected human tissue instantly. This enormous atmospheric pressure arises from the sheer mass of gas above Venus's surface. The total mass of Venus's atmosphere amounts to roughly 4.8 times 10 to the 20th power kilograms, which is about 92 times more massive than Earth's entire atmosphere. Venus's atmosphere presses down on every square meter of the surface with a force of approximately 9.3 million newtons, or about 940 metric tons. The density of the gas at the surface reaches approximately 65 kilograms per cubic meter, which is about 6.5% the density of liquid water. This makes Venus's atmosphere more than 50 times denser than Earth's atmosphere at sea level. The chemical composition of this dense atmosphere is remarkably simple in its major constituents. Carbon dioxide accounts for 96.5% of the atmospheric volume near the surface. This single molecule dominates the atmosphere to an extent seen nowhere else in the solar system among terrestrial planets. Earth's atmosphere, by comparison, contains only about 0.04% carbon dioxide, with nitrogen and oxygen making up most of the rest. Mars has an atmosphere that is 95% carbon dioxide, but that entire Martian atmosphere is extremely thin, with a surface pressure less than 1% that of Earth's. Nitrogen, the second most abundant gas in Venus's atmosphere, makes up approximately 3.5% by volume. On Earth, nitrogen constitutes 78% of our atmosphere and plays an essential role in the chemistry of life as we know it. The nitrogen molecules in Venus's atmosphere represent a significant reservoir of this element. Though in absolute terms, Venus has less total nitrogen than Earth due to Earth's much larger atmosphere when measured by mass rather than pressure at the surface. The remaining fraction of Venus's atmosphere consists of trace amounts of other gases. These include sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon. Sulfur dioxide exists at concentrations that vary with altitude, but typically measure around 150 parts per million in the lower atmosphere. This gas plays a crucial role in Venus's cloud formation and atmospheric chemistry, as we will explore shortly. Water vapor, surprisingly, exists at extremely low concentrations, roughly 30 parts per million or 0.003%. This makes Venus the driest planet in the inner solar system, with water content in its atmosphere orders of magnitude lower than even the driest deserts on Earth. The argon in Venus's atmosphere provides interesting clues about the planet's history. Venus has both argon-36, a primordial isotope left over from the solar system's formation, and argon-40, which forms from the radioactive decay of potassium-40 in rocks. The ratio of these argon isotopes, along with measurements of other noble gases, suggests that Venus has experienced significant outgassing from its interior over geological time, releasing volatiles trapped in rocks and bringing them to the surface. The abundance of primordial argon is higher on Venus than on Earth, which may indicate that Venus retained more of its original atmosphere or that Earth lost more of its early atmosphere through various processes. This carbon dioxide-dominated atmosphere creates what planetary scientists call a runaway greenhouse effect. To understand this, we need to consider how greenhouse gases interact with radiation. The Sun emits energy primarily in visible wavelengths, which pass relatively easily through carbon dioxide. When this sunlight reaches Venus's surface, it warms the rock and soil, which then emit thermal radiation in the infrared part of the spectrum, the same kind of heat radiation you feel from a warm stove. Carbon dioxide molecules absorb infrared radiation very effectively, trapping the heat energy in the atmosphere rather than allowing it to escape to space. On Earth, greenhouse gases like carbon dioxide and water vapor keep our planet warm enough to maintain liquid water on the surface, preventing Earth from being a frozen world. The greenhouse effect itself is not inherently problematic, it is actually essential for life as we know it. But on Venus, the concentration of carbon dioxide is so high that the greenhouse effect operates at an extreme level. Every infrared photon emitted by the hot surface gets absorbed within a short distance by carbon dioxide molecules in the atmosphere. These molecules then re-emit the energy, with some radiation going back down toward the surface and some continuing upward. But with such a dense atmosphere full of carbon dioxide, the energy has tremendous difficulty escaping to space. The result is that heat accumulates in the lower atmosphere and at the surface, driving temperatures to extraordinarily high levels. The surface temperature of Venus measures approximately 737 Kelvin, or 464 degrees Celsius, or 867 degrees Fahrenheit. To provide context, this temperature exceeds the melting point of lead, which melts at 600 Kelvin. It exceeds the melting point of zinc, which melts at 693 Kelvin. Tin melts at 505 Kelvin, well below Venus's surface temperature. If you could place a tin can on the surface of Venus, it would melt into a puddle. The temperature is hot enough that many chemical reactions that require high heat on Earth occur spontaneously on Venus's surface. What makes this temperature particularly remarkable is that Venus receives only about 75% as much solar energy as Earth does, owing to its greater distance from the Sun. Mercury, being much closer to the Sun, receives far more solar energy than Venus. Yet Venus's surface temperature exceeds even Mercury's maximum surface temperatures. Mercury's dayside can reach 700 Kelvin in some regions, but Venus maintains 737 Kelvin everywhere, day and night, equator and poles. The greenhouse effect more than compensates for Venus's greater distance from the Sun, making it the hottest planet in the solar system despite not being the closest to our star. This temperature remains remarkably constant across Venus's surface. Unlike Earth, where temperatures vary dramatically with latitude, longitude, time of day and season, Venus shows almost no variation in surface temperature. The difference between the dayside and nightside surface temperatures is essentially zero, perhaps varying by only a few degrees at most. The poles are no cooler than the equator. This uniformity results from several factors working together. First, Venus's extremely thick atmosphere conducts and circulates heat very efficiently, redistributing any temperature differences. Second, Venus's rotation is so slow that each face of the planet is exposed to sunlight for weeks at a time, giving the surface ample time to heat up. Third, the planet's axial tilt is only 2.64 degrees, meaning there are essentially no seasons, and the Sun's energy arrives at roughly the same intensity at all latitudes throughout the year. The combination of extreme temperature and pressure at Venus's surface creates an unusual state of matter. At 737 Kelvin and 93 bars, carbon dioxide exists above its critical point. The critical point of a substance is the temperature and pressure above which distinct liquid and gas phases cannot exist. Below the critical point, you can have either liquid carbon dioxide or gaseous carbon dioxide, with a clear boundary between them. Above the critical point, the substance enters what scientists call a supercritical fluid state, where it has properties intermediate between a liquid and a gas. It flows like a gas, but has a density closer to a liquid. Venus's lower atmosphere consists largely of supercritical carbon dioxide. This supercritical fluid has a density of approximately 65 kilograms per cubic meter, which allows it to erode rock surfaces in ways that normal gases cannot. When wind blows across Venus's surface, the high-density supercritical fluid can pick up and transport particles of rock and dust, causing weathering and erosion despite the relatively low wind speeds at ground level. This is one of the few processes that can modify Venus's surface in the absence of liquid water, which on Earth is the primary agent of erosion and sediment transport. The temperature and pressure conditions moderate somewhat as you ascend through Venus's atmosphere. The atmosphere is structured in layers much like Earth's, with a troposphere closest to the surface, followed by a mesosphere and a thermosphere at higher altitudes. In the troposphere, which extends from the surface up to about 65 kilometers, temperature decreases with altitude, following a steep gradient. By the time you reach an altitude of 50 kilometers, the temperature has dropped to approximately 340 Kelvin or 67 degrees Celsius, comfortably within the range of liquid water if any water were present. At 50 to 60 kilometers altitude, the pressure has likewise decreased to approximately 1 bar, the same as Earth's sea level atmospheric pressure. This creates a remarkable fact. There exists a region in Venus's atmosphere between roughly 50 and 65 kilometers above the surface, where both temperature and pressure closely match conditions at Earth's surface. A human could theoretically exist at this altitude in the Venusian atmosphere with only an oxygen supply and protection from the sulfuric acid in the clouds. This is the most Earth-like environment in the solar system outside of Earth itself, more hospitable in terms of temperature and pressure than the frozen surface of Mars or the airless terrain of the Moon. This zone of relative habitability exists within and just above Venus's global cloud deck. The clouds of Venus form a continuous, unbroken layer that completely obscures the surface from optical observations. These clouds extend from approximately 47 to 48 kilometers altitude up to about 70 kilometers, with the densest portions located around 48 to 50 kilometers. Above and below this main cloud deck, thinner hazes extend the visible cloud structure down to perhaps 32 kilometers and up to 90 kilometers. The composition of Venus's clouds was a mystery until 1973, when scientists determined that the cloud droplets consist primarily of sulfuric acid. Specifically, the clouds contain droplets of sulfuric acid and water in solution, with concentrations ranging from about 75% sulfuric acid and 25% water at the lower cloud layers to as high as 98% sulfuric acid at the upper cloud regions. The exact concentration varies with altitude as temperature changes affect the equilibrium between sulfuric acid, water, and sulfur-containing gases. Sulfuric acid forms in Venus's upper atmosphere through a series of photochemical reactions driven by solar ultraviolet radiation. The process begins with sulfur dioxide and carbon dioxide molecules. Ultraviolet photons split carbon dioxide molecules into carbon monoxide and atomic oxygen. The highly reactive atomic oxygen then combines with sulfur dioxide molecules to form sulfur trioxide. This sulfur trioxide combines with water vapor molecules to produce sulfuric acid. The reaction can be written as SO3 plus H2O yields H2SO4, and it occurs continuously in the upper atmosphere wherever sufficient sunlight, sulfur dioxide, and water vapor coexist. The newly formed sulfuric acid exists initially as vapor, but as the molecules cool and cluster together, they condense into tiny droplets. These droplets grow by accumulating more sulfuric acid molecules from the surrounding gas, and they can also coalesce when they collide with each other. Over time, the droplets grow large enough that gravity pulls them slowly downward through the atmosphere. They descend at speeds of roughly 1 millimeter per second, taking weeks or even months to fall from the cloud tops to the cloud base. As the droplets descend, they enter progressively warmer regions of the atmosphere. The increasing temperature causes the sulfuric acid to begin evaporating, releasing sulfur dioxide and water vapor back into the air. By the time the droplets reach the cloud base at around 47 kilometers altitude, where the temperature approaches 360 Kelvin, they have completely evaporated. The sulfur dioxide and water vapor continue descending into the hotter lower atmosphere, where they are eventually carried back up toward the cloud layer by atmospheric circulation. This creates a sulfur cycle in Venus's atmosphere, with sulfur compounds continuously moving between the upper cloud-forming regions and the lower atmosphere. The sulfuric acid droplets in Venus's clouds are remarkably small, typically measuring between 1 and 3 micrometers in diameter. For comparison, human hair ranges from about 50 to 100 micrometers in diameter, so these cloud droplets are more than 10 times smaller than a human hair is wide. Despite their small size, these droplets occur in such large numbers that they make the clouds very dense. The cloud density reaches approximately 0.1 grams per cubic meter at the densest levels, comparable to the density of cumulonimbus storm clouds on Earth. These clouds are highly reflective, bouncing back about 75% of the sunlight that strikes them. This high reflectivity, combined with the complete cloud coverage, gives Venus the highest albedo of any planet in the solar system. Albedo refers to the fraction of incident light that a surface or planet reflects, with 0 representing perfect absorption and 1 representing perfect reflection. Venus has a geometric albedo of approximately 0.75, meaning it reflects 3/4 of the sunlight that reaches it. This high reflectivity has interesting consequences. First, it explains why Venus appears so bright in our sky. The thick, highly reflective clouds make Venus one of the most brilliant objects visible from Earth. Second, despite being closer to the Sun than Earth, Venus's surface actually receives less solar energy than Earth's surface does, because the clouds reflect so much sunlight back to space before it can reach the ground. Below the clouds, in the lower atmosphere, conditions become progressively dimmer. At the surface, illumination levels measure approximately 14,000 lux, comparable to a heavily overcast day on Earth. While this is enough light to see by, it is much less than the 100,000 lux, typical of direct sunlight on Earth's surface. The thick atmosphere scatters and absorbs much of the remaining light that does penetrate the clouds, creating a perpetual twilight at ground level. The clouds themselves are not uniform. Spacecraft observations have revealed complex structures and patterns in the cloud deck. Dark, irregular patches appear in ultraviolet images of the clouds, caused by some compound that absorbs ultraviolet light. Scientists call this the unknown ultraviolet absorber, and its identity remains uncertain despite decades of research. Various substances have been proposed, including sulfur dioxide, elemental sulfur in different molecular forms, iron chloride, and even exotic organic compounds. Recent work suggests the absorber may be a mixture of multiple substances rather than a single compound. These dark ultraviolet patches organize themselves into distinct features, including a characteristic Y-shaped pattern that stretches across Venus's equatorial region, visible in many spacecraft images. The Y-shape and other cloud patterns rotate around the planet much faster than the planet itself rotates, a phenomenon we will examine when we discuss atmospheric circulation. The clouds also show variation in optical thickness and particle size with both altitude and location, creating the three-layer structure of the main cloud deck. The upper cloud layer, from roughly 60 to 70 kilometers altitude, contains the smallest droplets. The middle cloud layer, from 52 to 58 kilometers, contains medium-sized droplets and the highest concentration of cloud mass. The lower cloud layer, from 48 to 52 kilometers, contains larger droplets and marks the base of the main cloud deck. The continuous cloud cover and the scattering properties of the atmosphere combine to prevent almost all direct observation of Venus's surface using visible light from orbit or from Earth. Understanding what lies beneath the clouds required the development of radar technology, which can penetrate the atmosphere and clouds to map surface features. Ground-based radar observations began providing crude maps of Venus in the 1960s, and orbital radar missions vastly improved our knowledge in later decades. Venus's rotation presents one of the most peculiar characteristics of any planet in the solar system. The planet completes one rotation on its axis in 243.02 Earth days. This means that a single Venusian day, measured from one sunrise to the next as seen from the surface, would last an extraordinarily long time if the thick clouds did not prevent any direct view of the sun. But even more unusual than the slow rotation is its direction. Venus rotates in the opposite direction from most planets in the solar system, including Earth. Astronomers call this retrograde rotation. To understand what retrograde rotation means, imagine looking down on the solar system from high above the North Pole. From this vantage point, almost all planets, including Earth, rotate counterclockwise on their axes, while also orbiting counterclockwise around the Sun. Venus, however, rotates clockwise while orbiting counterclockwise. This means that if you could stand on Venus's surface and watch the sky, the Sun would rise in the west and set in the east, the opposite of the apparent solar motion we observe on Earth. Uranus also has a retrograde rotation, though Uranus is tilted so far over that its rotation axis lies nearly in the plane of its orbit, creating an entirely different situation. The slow, retrograde rotation of Venus creates an interesting relationship between different ways of measuring a day. A sidereal day represents the time it takes a planet to rotate once relative to the distant stars. For Venus, this sidereal day lasts 243.02 Earth days. However, a solar day represents the time between successive appearances of the Sun at the same position in the sky, such as from one noon to the next. Because Venus orbits the Sun while it rotates, and because it rotates in the opposite direction from its orbit, the solar day on Venus is much shorter than the sidereal day. A Venusian solar day lasts 116.75 Earth days. This means that on Venus, the Sun returns to the same position in the sky every 116.75 days, even though the planet takes 243.02 days to rotate once relative to the stars. Venus's year, the time it takes to complete one orbit around the Sun, is 224.7 Earth days. This creates the remarkable situation where a Venusian year is shorter than a Venusian sidereal day. The planet completes an entire orbit of the Sun in less time than it takes to rotate once on its axis. However, because the solar day is shorter than the year, approximately 1.92 solar days fit into one Venusian year. From the perspective of a hypothetical observer on the surface, the Sun would rise and set nearly twice during one trip around the Sun. Why does Venus rotate so slowly and in the opposite direction from most planets? This question has puzzled scientists since the rotation was first measured using radar in 1962. Several hypotheses have been proposed. One suggests that during Venus's formation, a large planetesimal collided with the proto-Venus with enough force to tip the planet over and alter its rotation. Computer simulations show that the right kind of impact could indeed flip a planet's rotation axis, though the details depend sensitively on the size, speed, and angle of the collision. Another factor involves Venus's dense atmosphere and its interaction with solar tides. The Sun exerts tidal forces on Venus that tend to slow the planet's rotation and eventually lock it so that the same face always points toward the Sun, much as the Moon always shows the same face to Earth. However, Venus's massive, rapidly circulating atmosphere creates additional forces on the surface. As the atmosphere heats up on the sunlit side of Venus, it expands and flows toward the night side, creating pressure imbalances that push on the surface. This atmospheric tide can, over very long timescales, counteract the Sun's tidal effects and even drive the planet's rotation in unexpected ways. Recent calculations suggest that Venus's current slow retrograde rotation may represent an equilibrium state where solar tides trying to stop or reverse the rotation are balanced by atmospheric tides maintaining the current rotation rate. The rotation rate itself has been measured to vary slightly over time. Observations taken by different spacecraft at different times show that the length of a Venusian day can change by several minutes over periods of years to decades. These variations probably result from changes in how angular momentum is exchanged between the solid planet and its atmosphere, a process similar to how Earth's rotation speed changes very slightly due to atmospheric circulation patterns, ocean currents, and the movement of ice masses. Venus's extremely slow rotation has profound consequences for the planet's lack of a magnetic field. Earth generates its magnetic field through a process called the dynamo effect, where the rotation of electrically conducting fluid in the planet's outer core generates electric currents, which in turn produce magnetic fields. This process requires sufficiently rapid rotation to organize the convecting fluid into the large-scale patterns necessary for field generation. Venus, despite likely possessing a metallic liquid outer core similar to Earth's, rotates too slowly to generate a significant dynamo. Measurements by various spacecraft have confirmed that Venus has no detectable intrinsic magnetic field. Without a planetary magnetic field, Venus's atmosphere interacts directly with the solar wind, the stream of charged particles constantly flowing outward from the sun. The solar wind carries its own magnetic field, and when it encounters Venus, it compresses the upper atmosphere and creates what scientists call an induced magnetosphere. The moving charged particles in the solar wind cannot easily cross magnetic field lines. So as the interplanetary magnetic field wraps around Venus, it creates a magnetic barrier that deflects most of the solar wind around the planet. This induced magnetosphere is much weaker and closer to the planet than Earth's magnetic field, which extends many tens of thousands of kilometers into space. On Venus, the induced magnetic boundary lies only a few hundred kilometers above the surface at the sub-solar point where the solar wind pressure is strongest. The lack of a strong magnetic field has consequences for atmospheric loss over geological time. Charged particles in the solar wind can interact with ions in Venus's upper atmosphere, providing energy that allows some atmospheric particles to escape to space. Over billions of years, this process has probably removed significant amounts of lighter elements from Venus's atmosphere. Measurements of isotope ratios in Venus's atmosphere provide evidence for this loss. For example, the ratio of deuterium to hydrogen in Venus's water vapor is much higher than the solar system's primordial ratio, suggesting that normal hydrogen has been preferentially lost to space over time, leaving behind a higher proportion of the heavier deuterium isotope. The atmosphere of Venus is not static, but moves in complex patterns driven by solar heating and the planet's rotation. The most striking feature of Venus's atmospheric circulation is the phenomenon known as superrotation. The entire atmosphere circulates around the planet from east to west in the same direction as the planet's rotation, but far faster than the surface rotates. At the cloud tops, at altitudes around 65 to 70 kilometers, wind speeds reach approximately 100 meters per second or 360 kilometers per hour. These winds circle the entire planet in approximately 4 Earth days, meaning the atmosphere completes a full rotation 60 times faster than the solid planet below it. This superrotation exists at all latitudes from the equator up to about 50 to 55 degrees latitude. The wind speed remains relatively constant throughout this equatorial and mid-latitude region, though it decreases gradually as you move toward higher latitudes. Beyond 55 degrees latitude, the winds slow dramatically, eventually reaching near zero speeds at the poles themselves. At the poles, the circulation pattern transforms into enormous vortex structures, polar vortices that rotate around each pole like gigantic hurricanes pinned to a single location. How Venus maintains this superrotation remains one of the enduring puzzles in planetary meteorology. The phenomenon cannot be explained by simple, thermal wind models that work well for Earth's atmospheric circulation. Instead, Venus's superrotation appears to require specific interactions between atmospheric waves, solar heating patterns, and the exchange of momentum between different layers of the atmosphere. Thermal tides, large-scale atmospheric waves driven by the daily cycle of solar heating, play a crucial role. As the sun heats the cloud tops during the long Venusian day, the atmosphere expands and contracts, creating waves that propagate vertically and horizontally. These waves transport angular momentum from the lower atmosphere upward and from the equatorial regions poleward, gradually spinning up the upper atmosphere to speeds far exceeding the rotation of the surface. The solar heating pattern on Venus differs significantly from Earth's. Because Venus rotates so slowly, each point on the planet experiences continuous sunlight for approximately 58 Earth days, followed by 58 days of darkness. This creates a moving hotspot that tracks with the sun's position in the sky, always remaining directly below the sun. The atmosphere responds to this moving heat source by organizing circulation patterns that follow the sun, with warm air rising in the heated regions and cooler air descending elsewhere. This creates thermal tides that encircle the planet, and the interaction between these tides and the planet's rotation generates the forces that maintain superrotation. At lower altitudes, the winds decrease substantially. By the time you descend to the surface, wind speeds measure only around 0.3 to 1 meter per second or 1 to 4 kilometers per hour. These are gentle breezes by Earth standards, barely enough to disturb leaves on a tree. However, as mentioned earlier, the extreme density of Venus's lower atmosphere means that even these slow-moving winds exert considerable force and can transport particles and cause erosion. The wind momentum, the product of density and velocity, remains significant even though the velocity is low. The circulation pattern in Venus's atmosphere follows what atmospheric scientists call a Hadley circulation, modified by the planet's slow rotation and super-rotating upper atmosphere. In a Hadley cell, air rises in heated equatorial regions, flows toward the poles at high altitude, descends in cooler polar regions, and returns toward the equator at low altitude. Earth has 3 circulation cells in each hemisphere due to Earth's faster rotation, but Venus's slow rotation allows a single planet-wide circulation cell to form in each hemisphere. Warm air rises near the equator, flows poleward at cloud-top levels at speeds near 100 meters per second, gradually descends as it moves poleward, and then returns toward the equator in the lower atmosphere. The descending branch of the circulation reaches the surface at mid to high latitudes and flows slowly back toward the equator close to the ground. This slow, return flow carries heat from the equator toward higher latitudes, contributing to the remarkable temperature uniformity across Venus's surface. The circulation also transports trace gases and aerosols, redistributing sulfur compounds, water vapor, and other minor atmospheric constituents between different regions and altitudes. Embedded within this large-scale circulation are various waves and disturbances that create complex patterns in the cloud deck. Gravity waves, not to be confused with gravitational waves, are oscillations that occur in the atmosphere when air is displaced vertically and then restored by buoyancy forces. These waves propagate horizontally and vertically through the atmosphere, transferring energy and momentum. Venus's atmosphere shows abundant gravity wave activity, particularly in the region between the middle cloud deck and the upper cloud tops. These waves appear in spacecraft images as ripples, streaks, and complex structures within the broader cloud. Patterns. The polar vortices represent another dramatic feature of Venus's atmospheric circulation. At each pole, the descending air from the Hadley circulation creates a rotating structure that resembles a hurricane or cyclone. The southern polar vortex has been observed in detail by several spacecraft, including Venus Express. The vortex forms a distinctive S-shaped or figure-8 pattern of clouds that rotates around the pole once every 2 to 3 Earth days. The structure remains relatively stable in its overall form, but undergoes continual changes in detail, with smaller vortices and filaments appearing, merging, and dissipating within the larger circulation. Temperature measurements show that the polar regions have a warm core, warmer than the surrounding atmosphere at the same altitude. This warmth results from the descending air in the polar vortices. As air descends, atmospheric pressure compresses it, and compression heats the gas. This adiabatic warming creates the elevated temperatures observed at the poles, despite the poles receiving less solar energy than equatorial regions. The warm polar temperatures represent another factor contributing to Venus's global temperature uniformity. The study of Venus's atmospheric dynamics benefits tremendously from continuous monitoring by spacecraft. The Venus Express mission orbited Venus for 8 years, providing an unprecedented long-term dataset of atmospheric temperatures, wind speeds, cloud patterns, and chemical compositions. One significant discovery from Venus Express was the extreme variability of the southern polar vortex. The vortex shape could transform from a single centered circulation to a double vortex structure with 2 distinct rotation centers, and back again over timescales of days to weeks. This variability suggests complex interactions between the large-scale Hadley circulation, smaller-scale wave phenomena, and perhaps the underlying topography that creates stationary waves in the atmosphere. Understanding the circulation of Venus's atmosphere helps explain how the planet maintains such uniform surface temperatures despite receiving uneven solar heating. The slow rotation means each hemisphere experiences weeks of continuous daylight followed by weeks of darkness. Yet the surface temperature hardly changes between day and night. The massive atmosphere acts as a tremendous reservoir of thermal energy. Even when the night side receives no solar energy, the atmosphere contains so much heat and circulates it so effectively from the day side that surface temperatures remain constant. The transport of heat by atmospheric circulation, combined with the enormous greenhouse effect that traps heat at the surface, creates a thermal bath that smooths out any local temperature variations. Beneath this dynamic, cloud-covered atmosphere lies the surface of Venus, a landscape shaped by volcanic processes operating on a global scale. The surface of Venus is relatively young compared to most rocky bodies in the solar system. Impact crater counts suggest that the surface has an average age of only 300 to 600 million years, quite recent in geological terms. For comparison, portions of the lunar highlands date back over 4 billion years, and large areas of Mars preserve surfaces several billion years old. Venus's relatively crater-free surface indicates that volcanic activity has resurfaced the planet, covering up older impact craters with fresh lava flows. The exact mechanism and timing of this resurfacing remain subjects of active research. Some scientists propose that Venus undergoes periodic global resurfacing events, where massive volcanic eruptions erupt across much of the planet's surface over a relatively short geological time, perhaps 10 million to 100 million years, burying the old surface under new volcanic material. After such an event, volcanic activity would decline to low levels until heat building up in the mantle triggers the next resurfacing event hundreds of millions of years later. This model, called catastrophic resurfacing, would explain the lack of very old terrains and the relatively uniform age of the current surface. Alternative models suggest that volcanism on Venus continues at a more steady but lower rate, with volcanic eruptions occurring frequently enough to gradually renew the surface over time. Under this gradual resurfacing scenario, we happen to observe Venus at a time when its average surface age is a few 100 million years, but the age distribution includes both younger and older terrains. Recent observations have provided some evidence for ongoing volcanic activity, including changes in sulfur dioxide concentrations that could result from fresh volcanic eruptions releasing new gases into the atmosphere, and possible detection of thermal hotspots that might represent active lava flows. However, definitive proof of current volcanism requires more detailed observations than have been obtained to date. The surface itself consists primarily of volcanic plains, vast expanses of relatively flat terrain covered by solidified lava flows. These plains account for roughly 90% of Venus's surface area. Radar imaging from orbit reveals that the plains contain numerous overlapping flow features, channels, and other structures characteristic of basaltic lava, the same type of dark, iron-rich volcanic rock that forms the ocean floor on Earth and covers large areas of the lunar maria. The lava flows on Venus extend for hundreds or sometimes thousands of kilometers, indicating eruptions that released enormous volumes of molten rock. The remaining 10% of the surface consists of several types of features. Highland regions, elevated areas that rise above the surrounding plains, cover about 8% of the surface. The most prominent highlands are Ishtar Terra in the northern hemisphere and Aphrodite Terra in the equatorial region. Ishtar Terra contains Maxwell Montes, the highest mountain range on Venus, which reaches an elevation of approximately 11 kilometers above Venus's mean radius. Maxwell Montes shows characteristics suggesting it may have formed through tectonic compression, where large-scale forces push the crust together and upward, similar to how the Himalayas formed on Earth. However, the exact mechanism remains uncertain given Venus's apparent lack of plate tectonics. Aphrodite Terra stretches nearly 10,000 kilometers along Venus's equator, roughly the length of North America. This highland region contains complex terrain, including mountains, deep valleys, and evidence of extensive tectonic deformation. The valleys within Aphrodite Terra, particularly Diana Chasma and Dali Chasma, drop several kilometers below the surrounding terrain and extend for thousands of kilometers, resembling rift valleys where the crust has been pulled apart. Scattered across Venus's plains and highlands are volcanic features of remarkable diversity and scale. Venus has more volcanoes than any other planet in the solar system, with over 1,600 major volcanoes identified, defined as those with diameters exceeding 20 kilometers. Beyond these major edifices, countless smaller volcanic features dot the surface. The volcanoes on Venus show characteristics suggesting they formed from relatively fluid basaltic lava, which flows easily and spreads out over large areas before solidifying. Shield volcanoes, broad structures with gently sloping sides, built up by countless eruptions of fluid lava, appear commonly on Venus. These resemble Hawaiian shield volcanoes on Earth, though some Venusian shields reach truly immense proportions. Mont Mons, the tallest volcano on Venus, rises approximately 8 kilometers above the mean radius and spans about 400 kilometers across at its base. Sapas Mons, Oza Mons, and numerous other shields create distinctive features visible in radar imaging. A type of volcanic feature particularly characteristic of Venus is the pancake dome. These are flat-topped, steep-sided circular structures ranging from a few tens of kilometers in diameter up to 100 kilometers across. They appear to have formed from viscous lava, perhaps rich in silica, that extruded onto the surface and spread out into circular domes before solidifying. The lava was thick enough that it didn't flow far from the eruption site, creating the steep sides, but fluid enough to spread into relatively flat-topped shapes. Dozens of pancake dome fields exist on Venus, with individual domes sometimes clustered in groups. Perhaps the most distinctive features on Venus are coronae, large circular to oval structures surrounded by concentric ridges and troughs. Coronae range from 150 to over 1,000 kilometers in diameter, and more than 500 have been identified. They appear to form where rising plumes of hot material from deep within Venus's mantle push upward on the crust, creating a dome. As the plume spreads out beneath the crust, it creates the characteristic concentric fracture patterns. Eventually, the plume may break through the surface, causing volcanic eruptions within the corona. Some coronas show evidence of collapse in their centers, possibly after the underlying plume withdrew or cooled, leaving the overlying crust unsupported. Another category of Venusian features is arachnoids, networks of fractures radiating outward from central points, often associated with small volcanic edifices. The name derives from their spiderweb-like appearance in radar images. They may represent earlier stages of corona formation or separate volcanic features created by smaller mantle plumes. The intense heat and pressure at Venus's surface create unusual weathering conditions. Certain minerals that are stable at Earth's surface temperatures decompose or alter their structure at Venusian temperatures. Laboratory experiments have shown that many silicate minerals develop surface coatings or undergo chemical changes that could alter the surface's reflectivity and chemical properties. Some researchers have proposed that minerals containing iron could become coated with thin layers of magnetite or other iron oxide minerals, changing the rock's electrical properties in ways that might explain unusual radar characteristics observed in highland regions. The Venera landers that successfully reached Venus's surface and transmitted data back to Earth provided the only direct measurements we have of surface rock chemistry. Venera 13 and 14, which landed in 1982, carried instruments that measured the chemical composition of the rocks at their landing sites. The results showed material consistent with basaltic composition, similar to the rocks forming Earth's oceanic crust and the Luna Maria. The rocks contained approximately 45 to 48% silicon dioxide, 8 to 11% aluminum oxide, 7 to 16% iron oxide, and several percent each of calcium oxide and magnesium oxide. These proportions fall within the range expected for basaltic rocks formed from partial melting of a rocky mantle. The landers also captured the only photographs ever obtained from Venus's surface. These images show rocky, slab-like fragments of rock scattered across a dark plain. The lighting is dim but adequate to see the surroundings. The flat slabs of rock may represent broken pieces of lava flows or ejecta from impact craters. The sky appears orange or yellow-orange in the images, a color resulting from the scattering of light by the dense atmosphere and the chemical composition of the cloud particles and atmospheric gases. The extreme heat destroyed each lander within a few hours of reaching the surface. The Venera spacecraft were designed with extensive thermal insulation and cooling systems to keep their internal electronics functional for as long as possible, but eventually the heat penetrated the insulation and the electronics failed. The longest surviving lander, Venera 13, transmitted data for 127 minutes after landing before succumbing to the brutal conditions. No spacecraft has landed on Venus since 1984, and no surface rover has ever been deployed. The technical challenges of building a rover that could function for more than a few hours in Venus's environment remain formidable. Electronics malfunction at temperatures above about 125 degrees Celsius unless specially designed with high-temperature semiconductors, and mechanical systems face challenges from the heat and pressure as well. Recent technological advances in high-temperature electronics and materials have renewed interest in designing long-duration Venus surface missions. But as of now, all our detailed knowledge of the surface comes from orbital radar mapping and the brief glimpses provided by the Venera landers. The question of active volcanism on Venus takes on particular importance when considering the planet's evolution and current state. Detection of ongoing eruptions would provide crucial information about Venus's internal heat flow and the dynamics of its mantle. Several lines of evidence suggest that volcanism may be continuing today. Measurements of sulfur dioxide concentrations in Venus's upper atmosphere have shown significant variations over timescales of years to decades. Sulfur dioxide decreases with altitude due to chemical reactions that convert it to sulfuric acid, creating a concentration gradient. However, the overall amount of sulfur dioxide in the middle and upper atmosphere has been observed to vary by factors of 2 to 3. If volcanic eruptions periodically inject fresh sulfur dioxide into the atmosphere, the concentration would spike upward and then gradually decline as chemical reactions remove the gas, explaining the observed variations. Alternative explanations involving changes in atmospheric circulation or cloud chemistry cannot be completely ruled out, but volcanism remains the most straightforward interpretation. Unfortunately, the temporal coverage of measurements is insufficient to detect individual eruption events definitively. Another line of evidence comes from thermal emission measurements. Spacecraft instruments designed to detect infrared radiation emitted by the hot surface have found several locations where the thermal emission appears anomalously high, suggesting temperatures above the normal 737 Kelvin surface temperature. If these hotspots are real and not instrumental artifacts, they could represent fresh lava flows that have not yet cooled to equilibrium with their surroundings. However, alternative explanations involving differences in surface composition or texture affecting the emissivity could also explain the observations. The search for active volcanism on Venus continues with each new mission. Future missions equipped with higher resolution imaging systems and more sensitive instrumentation may finally provide definitive detection of volcanic eruptions or lava flows in progress. Understanding the current level of volcanic activity would help constrain models of Venus's interior structure and thermal evolution, answering questions about whether Venus is still volcanically vibrant or has entered a period of reduced activity. The absence of water on and in Venus stands as one of the most fundamental differences between Venus and Earth. Earth's surface is 70% covered by liquid water oceans, with additional water locked in ice caps, glaciers, groundwater, lakes, and rivers. Water vapor constitutes a variable but significant fraction of Earth's atmosphere, typically around 0.4% globally averaged, but reaching several percent in tropical regions. The total amount of water on Earth, if gathered together, would form a sphere approximately 1,400 kilometers in diameter. Venus has almost none of this. The 30 parts per million of water vapor in Venus's atmosphere represents only a tiny fraction of Earth's atmospheric water, and no evidence exists for liquid water or ice anywhere on or in the planet. The total amount of water on Venus, if gathered together, would form a layer only a few centimeters deep if spread over the planet's surface. Earth's oceans, by comparison, average about 4 kilometers deep. This extreme dryness raises the question of whether Venus ever had more water in the past. The deuterium to hydrogen ratio in Venus's atmospheric water provides crucial evidence. Deuterium, the heavy isotope of hydrogen, contains 1 proton and 1 neutron in its nucleus, compared to normal hydrogen's single proton. Water molecules can contain either normal hydrogen or deuterium, forming regular water, semi-heavy water, or heavy water in Venus's atmosphere. The ratio of deuterium to hydrogen is approximately 150 times higher than the ratio measured in Earth's oceans. This isotopic enrichment points toward a history of substantial water loss. Ultraviolet radiation from the Sun can split water molecules in Venus's upper atmosphere into hydrogen and oxygen atoms. The hydrogen atoms, being very light, can reach high enough speeds from collisions with other particles that they escape Venus's gravitational pull and are lost to space. Deuterium atoms, being twice as heavy, escape much more slowly. Over billions of years, if Venus started with water that had the same deuterium ratio as Earth's water, the preferential loss of normal hydrogen would progressively increase the deuterium to hydrogen ratio in the remaining water. Calculations suggest that to reach Venus's current deuterium enrichment, the planet must have lost an amount of water equivalent to at least the content of a shallow ocean, perhaps several tens of meters deep if spread uniformly over the surface. Some estimates suggest Venus could have had as much water as Earth in its earliest history, with all of it eventually lost to space through the process described above. Why did Venus lose its water while Earth retained its oceans? The answer appears to involve Venus's proximity to the Sun. In the early solar system, the Sun was slightly cooler than it is today, but even so, Venus received significantly more solar energy than Earth due to its closer orbit. This extra heating made it more difficult for water to condense into liquid form on Venus's surface. Instead, water remained in the atmosphere as vapor, where solar ultraviolet radiation could dissociate it. On Earth, water condensed into oceans that covered the surface. This removal of water vapor from the atmosphere limited the greenhouse effect, keeping temperatures moderate. The oceans also dissolved carbon dioxide from the atmosphere, which eventually became locked into carbonate rocks through chemical weathering and biological processes. This removed much of the atmospheric carbon dioxide, further moderating Earth's greenhouse effect. On Venus, without liquid water to remove carbon dioxide from the atmosphere, the carbon dioxide accumulated, strengthening the greenhouse effect and heating the planet further. This prevented any remaining water from condensing, creating a positive feedback that led to the runaway greenhouse state we observe today. All the carbon dioxide that on Earth became locked in limestone and other carbonate rocks remained in Venus's atmosphere, creating the dense, carbon dioxide-dominated envelope we measure today. This divergence between Earth and Venus's evolution illustrates how sensitive planetary climate can be to initial conditions and feedback processes. A relatively small difference in solar heating, combined with the presence or absence of liquid water, led to completely different evolutionary paths for two otherwise very similar planets. Venus ended up hot, dry, and cloud-covered, while Earth developed moderate temperatures, liquid water oceans, and eventually life. The possibility of past liquid water on Venus has interesting implications for astrobiology. If Venus had liquid water on its surface for an extended period in its early history, perhaps hundreds of millions or even a billion years, conditions might have been suitable for life to arise. The early sun's lower luminosity could have kept Venus cool enough for liquid water during the solar system's first billion years. Life might have emerged in that ancient Venusian ocean just as it did in Earth's oceans. If life did arise on early Venus, it would have faced increasing stress as the greenhouse effect intensified and the oceans evaporated. Some organisms might have adapted to progressively hotter and drier conditions, potentially finding refuge in the clouds as the surface became uninhabitable. This has led to speculation about possible microbial life existing today in Venus's cloud layer, where temperature and pressure conditions are relatively moderate. The cloud droplets, despite being concentrated sulfuric acid, might provide a niche where specially adapted microorganisms could survive, perhaps metabolizing sulfur compounds or other chemicals in the atmosphere. This speculation received renewed attention in 2020 when researchers reported the detection of phosphine gas in Venus's atmosphere. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, is produced on Earth primarily through biological processes involving anaerobic bacteria, though it can also be created through certain geological or chemical processes. The reported detection of phosphine at concentrations of around 20 parts per billion in Venus's cloud layer initially created excitement about the possibility of life in Venus's atmosphere. However, subsequent analysis questioned whether the detection was real, with some researchers suggesting the spectroscopic signals attributed to phosphine could instead result from sulfur dioxide or other molecules. The debate over phosphine detection highlights both the challenges of observing Venus's atmosphere and the intense interest in understanding whether Venus might harbor life. As of now, the question remains unresolved, awaiting new observations and missions with instruments specifically designed to search for phosphine and other potential biosignature gases. Regardless of whether life exists on Venus today, the planet serves as an important example for understanding habitability and climate evolution on rocky planets. The study of Venus helps us understand the range of possible outcomes for terrestrial planets and provides crucial data for assessing potentially habitable exoplanets orbiting other stars. Astronomers have discovered thousands of exoplanets, many of which are rocky worlds with sizes similar to Venus and Earth. Some orbit their stars at distances that place them near the inner edge of the habitable zone, where liquid water might or might not be stable on their surfaces, depending on atmospheric composition and greenhouse effect strength. Venus demonstrates that a planet very similar to Earth in size and composition can end up in a completely different state if conditions push it across certain thresholds. Understanding exactly where those thresholds lie and what feedback mechanisms can drive a planet from one state to another is essential for predicting which exoplanets might support life and which might be Venus-like worlds hidden beneath reflective clouds. The relationship between Venus and Earth, as viewed from Earth, adds another dimension to the planet's significance. As mentioned at the beginning, Venus and Earth engage in an orbital dance that brings them into similar geometric configurations every 8 Earth years. This near commensurability of orbital periods means that after exactly 8 years, Venus has completed almost exactly 13 orbits, while Earth has completed 8, and the two planets return to nearly the same relative positions. The ratio of 13 to 8 is approximately 1.625, which is very close to the golden ratio of 1.618 that appears throughout mathematics and nature. When mapped over many years, the points of closest approach between Venus and Earth trace a 5-petaled pattern in space due to this 13-to-8 orbital resonance. Each petal represents one of the 5 conjunctions that occur over the 8-year cycle. This creates a beautiful geometric relationship between the two planets, a pattern that ancient astronomers observed and incorporated into their calendars and cosmologies. The phases of Venus, first observed by Galileo, also create a regular pattern in our sky. When Venus lies on the far side of the Sun from Earth, it appears nearly full, showing its entire illuminated hemisphere toward us. However, at this configuration, called superior conjunction, Venus is at its greatest distance from Earth and appears small in telescopes. As Venus moves around its orbit, it gradually approaches Earth. As it gets closer, more of its night side faces toward us, and we see it progress through phases from full to gibbous to half-illuminated to crescent. At the same time, because Venus is getting closer, its apparent size increases. By the time Venus reaches inferior conjunction, passing between Earth and the Sun, it appears as a very large but thin crescent, nearly 30 times larger in angular diameter than when it was full. This inverse relationship between phase and apparent size means that Venus appears brightest in our sky not when it is full, but when it is a large crescent. At maximum brightness, which occurs about 36 days before and after inferior conjunction, Venus shows about a quarter of its illuminated hemisphere to us, appearing roughly 40% illuminated, but its proximity makes it appear much larger than when full. At this optimal combination of size and phase, Venus reaches an apparent magnitude of about -4.6, bright enough to cast faint shadows on Earth on very dark, clear nights. The visibility of Venus follows a predictable pattern through the year due to its orbit. For several months, Venus appears as an evening star, visible in the western sky after sunset. During this period, it rises to a maximum angular separation from the Sun of about 47 degrees, which translates to appearing up to about 3 hours behind the Sun at sunset, providing ample time for observation in the evening sky. As the weeks pass, Venus gradually descends back toward the Sun in our view, eventually passing through inferior conjunction and disappearing in the Sun's glare for a few days. Then Venus emerges on the other side of the Sun, reappearing as a morning star in the eastern sky before dawn. It rises progressively, earlier each morning, reaching a maximum separation of 47 degrees from the Sun on this side, appearing up to 3 hours before sunrise. Then it gradually sinks back toward the Sun, disappearing in the dawn twilight, passes through superior conjunction on the far side of the Sun, and emerges again in the evening sky to repeat the cycle. This complete cycle, from one appearance as evening star through morning star and back to evening star, takes the 584-day synodic period. Ancient astronomers tracked these appearances meticulously. The Babylonians recorded observations of Venus on clay tablets dating back thousands of years, noting its appearances and disappearances with precision. The Mayans integrated Venus into their calendar systems, recognizing its synodic period and assigning it great significance in their cosmology. The recognition that the evening star and morning star were the same object, Venus, apparently occurred independently in several ancient cultures, demonstrating the sophistication of early astronomical observation. From a modern perspective, understanding Venus's orbit and motion helps us appreciate the clockwork regularity of planetary mechanics. The gravitational interactions that maintain Venus in its nearly circular orbit have operated unchanged for billions of years. The same orbital period that brings Venus around the Sun every 224.7 days has likely remained constant to within tiny fractions of a percent since the solar system settled into its current configuration. This stability extends to other aspects of Venus's orbit. The orbital plane of Venus is tilted only 3.4 degrees relative to Earth's orbital plane, keeping Venus close to the ecliptic as seen from Earth. This small inclination means Venus transits across the face of the Sun as seen from Earth occasionally, an event that occurs in pairs separated by 8 years, with each pair separated from the next by over a century. The last transit pair occurred in 2004 and 2012, and the next will not happen until 2117 and 2125. These transits played an important role in the history of astronomy. In the 17th and 18th centuries, astronomers realized that careful timing of Venus, transits from different locations on Earth, could be used to calculate the distance from Earth to the Sun, the astronomical unit. Edmund Halley proposed this method in 1696, and during the transits of 1761 and 1769, international efforts sent astronomers to remote locations around the globe to observe and time the transit precisely. Though the calculations were complex and the results varied, these observations provided some of the first reasonably accurate measurements of the astronomical unit, helping establish the scale of the solar system. The orbital stability of Venus contrasts with the extreme conditions on its surface and in its atmosphere. While the greenhouse effect, volcanic activity, and atmospheric circulation create a dynamic and harsh environment, the orbit itself represents a zone of constancy. Venus has circled the Sun in this same path for eons, will continue for eons more, maintained in its trajectory by the gravitational influence of the Sun modulated slightly by the other planets. The gravitational perturbations from Jupiter, Earth, and other planets cause Venus's orbit to vary slowly over timescales of thousands to millions of years, but these changes are small and occur within predictable ranges. Venus's lack of large moons also contributes to its orbital and rotational stability over geological time. Earth's moon is massive enough relative to Earth that the Earth-Moon system is sometimes described as a double planet. The Moon stabilizes Earth's rotational axis, preventing it from wandering significantly over millions of years and maintaining relatively stable seasonal patterns. Venus has no large moon to provide this stabilization. Small orbital perturbations from the Sun and planets can affect Venus's rotation axis over very long time scales. Astronomers have calculated that Venus's obliquity, the tilt of its rotation axis relative to its orbital plane, has likely varied over geological time. Currently, Venus's obliquity is 177.4 degrees, which represents an axial tilt of 2.6 degrees, but with the rotation axis tipped over past the 90-degree point, resulting in the retrograde rotation. Without a large moon to stabilize this axis, chaotic changes could have moved it through a range of values over billions of years. Some researchers have suggested that Venus might have experienced large variations in obliquity in its past, which could have influenced climate patterns and atmospheric evolution, though the thick atmosphere would have damped out most seasonal effects, even with higher obliquity. The question of whether Venus ever had a moon remains open. Some models of Venus's formation suggest it could have had one or more moons in the distant past that were later lost through orbital decay, collision, or ejection. The retrograde rotation might even result from a giant impact similar to the one thought to have formed Earth's moon, though with different orbital dynamics that led to retrograde rather than prograde rotation. Without rock samples to analyze or detailed knowledge of Venus's internal structure, these scenarios remain speculative. Looking toward Venus from the perspective of future exploration, several missions are planned or under consideration for the coming decades. NASA has selected 2 missions to Venus as part of its Discovery program. Da Vinci, the Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, will send a probe descending through Venus's atmosphere, making detailed measurements of composition, temperature, and pressure as it falls toward the surface. The probe will also take high-resolution images during its descent, providing new views of the Venusian terrain. Veritas, Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy will orbit Venus and use radar to create high-resolution topographic maps of the surface, study surface composition using infrared spectroscopy, and precisely measure Venus's gravitational field to understand its internal structure. The European Space Agency has also selected ENVISION, another Venus orbiter mission, to study the planet's atmosphere, surface, and interior. ENVISION will carry instruments to analyze the atmosphere's composition and dynamics, map surface mineralogy, and use radar to study geological features. These missions together will provide the most comprehensive examination of Venus since the Magellan mission in the 1990s. India's space agency ISRO is developing Shukrayan, an orbiter mission to Venus that would study the surface and atmosphere using various instruments. Russia has discussed plans for Venera D, which would include an orbiter, lander, and possibly atmospheric balloons to study Venus comprehensively. These planned missions reflect renewed international interest in Venus exploration, driven partly by the intriguing questions about past habitability, possible current microbial life in the clouds, and the broader importance of Venus for understanding terrestrial planet evolution. A particularly innovative concept involves long-duration balloon or airship missions that would float in Venus's upper atmosphere at the altitude where conditions are most Earth-like. At 55 kilometers altitude, the temperature is around 27 degrees Celsius, and the pressure is about half of Earth's sea level pressure. A habitat designed for this environment would need protection from sulfuric acid in the clouds, but would not require the extreme thermal protection and pressure resistance necessary for the surface. Humans could potentially explore this region directly, floating above the hostile surface in aircraft or balloons, studying the atmosphere and clouds in detail. While no such missions are currently funded, the concept has been studied extensively and remains a possibility for the future. The scientific value of studying Venus extends beyond simply understanding one more planet. Venus represents an alternative outcome for planetary evolution, a case study in how initial conditions and feedback processes can push a terrestrial planet into a state very different from Earth's. Every measurement we obtain from Venus, every observation of its atmospheric circulation, surface geology, or isotopic composition provides data that tests our theories of how planets work. These theories apply not just to Venus and Earth, but to the thousands of rocky exoplanets we are discovering around other stars. When astronomers detect a rocky exoplanet orbiting in the inner region of its star's habitable zone, understanding Venus becomes crucial for interpreting what that planet might be like. Is it an Earth-like world with oceans and moderate climate, or is it a Venus-like world with runaway greenhouse conditions and a crushing atmosphere? The answer depends on factors we are still working to fully understand: the planet's initial water content, the strength of its greenhouse effect, the behavior of its atmosphere, and possibly the presence or absence of plate tectonics, magnetic fields, and other properties we can measure on Venus but cannot yet measure on distant exoplanets. In this way, Venus serves as a laboratory where we can study processes that occur on many worlds. The runaway greenhouse effect, superrotation, cloud formation from sulfuric acid, volcanic resurfacing, and atmospheric escape all operate on Venus in ways we can observe and measure. By understanding these processes on Venus, we build the knowledge needed to interpret observations of exoplanets and to assess which worlds might be habitable and which might be hostile to life. The role of Venus in our solar system has additional dimensions beyond the purely scientific. Culturally, Venus has influenced human thought for millennia. Its brilliance in our sky has inspired countless myths, poems, and artistic works. Ancient peoples associated Venus with deities of love and beauty, recognizing something special in this bright wanderer that appeared both before dawn and after dusk. The regular patterns of its appearances and disappearances, its changing phases and brightness, provided early astronomers with challenges that drove the development of observational techniques and mathematical models of planetary motion. The realization that the evening star and morning star were the same object represented an important step in human understanding of the cosmos. The observation of Venus's phases by Galileo provided crucial evidence for the heliocentric model of the solar system, helping overthrow the geocentric view that had dominated Western thought for centuries. The use of Venus transits to measure the astronomical unit demonstrated the power of international scientific cooperation and precise measurement. Each of these developments expanded human knowledge and changed our perception of our place in the universe. In modern times, Venus continues to challenge and inspire. The extreme conditions on its surface push the boundaries of engineering and material science, driving innovations in high-temperature electronics and robust spacecraft design. The puzzles of its atmospheric superrotation and possible active volcanism provide ongoing research opportunities for planetary scientists. The question of whether life exists in Venus's clouds keeps astrobiologists engaged. The comparison between Venus and Earth informs our understanding of climate change and greenhouse effects, offering a stark example of how atmospheric composition affects planetary temperature. As we look at Venus through a telescope, seeing that brilliant point of light that has captivated humanity for thousands of years, we can appreciate both what we know and what remains to be discovered. We know Venus's size precisely, down to the kilometer. We know its atmospheric pressure to within a fraction of a bar. We know the speed of its cloud-top winds, the composition of those clouds, the temperature at its surface, and the length of its day. We have mapped its volcanic plains and measured its lack of a magnetic field. We have detected trace gases in its atmosphere and calculated how much water it has lost over billions of years. Yet, significant mysteries remain. We do not know whether volcanoes are erupting on Venus's surface right now. We do not fully understand what drives the superrotation of the atmosphere or what causes the variations in the polar vortex structure. We have not identified the ultraviolet absorber that creates dark patterns in the clouds. We do not know whether microbial life exists in the cloud layer or whether life ever existed on an earlier, wetter Venus. We do not understand the full details of how Venus's surface gets resurfaced or how often this occurs. We have not determined exactly what drives the variations in Venus's rotation rate. These remaining questions ensure that Venus will continue to be a target of exploration and study for decades to come. Each new mission will answer some questions and inevitably raise new ones. Each measurement will refine our understanding and reveal new complexities. This is the nature of scientific exploration. The more we learn, the more we realize how much remains to be understood. For now, Venus continues its eternal orbit, circling the Sun every 224.7 days, rotating slowly backward on its axis every 243 days, maintaining its crushing atmosphere of carbon dioxide, its sulfuric acid clouds, its scorching surface temperature. The winds at the cloud tops race around the planet every 4 days while the surface winds barely stir. Volcanic plains cover 9/10 of the surface, while highland regions rise several kilometers above the mean radius. The atmosphere superrotates, the polar vortices swirl, and trace gases cycle between the surface and the upper atmosphere. All of this occurs on a world so similar to Earth in size and mass that the two planets are often called twins. Yet their surfaces could hardly be more different. One world has oceans, continents, plate tectonics, a magnetic field, moderate temperatures, and abundant life. The other has a dry volcanic surface, no plate tectonics, no magnetic field, hellish temperatures, and possibly no life at all. The comparison invites contemplation about what makes a planet habitable, how small changes can lead to dramatically different outcomes, and how fortunate we are that Earth followed the path it did. When you see Venus shining in the evening sky or before dawn, remember that you are looking at a world that shares our solar system, formed from the same cloud of gas and dust that created Earth, yet evolved along a fundamentally different path. You are seeing sunlight reflecting off clouds of sulfuric acid droplets in an atmosphere 90 times denser than ours, circulating around a planet that rotates backward beneath them. You are seeing a world that once might have had oceans but lost them billions of years ago. A world that resurfaces itself through volcanism on a scale that dwarfs anything on Earth. A world that poses profound questions about climate, geology, and the limits of habitability. This brilliant point of light, brighter than any star, brighter than any planet, except when Mars makes its closest approaches, has drawn human attention for as long as we have looked upward. It will continue to shine in our sky for billions of years to come, following its nearly circular orbit with the same mathematical precision that has governed its path since the solar system formed. Its brightness will vary with its phases and its distance from Earth, appearing now in the evening, now in the morning, tracing that elegant 5-petaled pattern through the decades. The stability of that pattern, the predictability of those orbital mechanics, provides a kind of cosmic reassurance. Venus will be there, circling the Sun, whether we observe it or not, whether we send missions to study it or not, whether we solve its mysteries or leave them for future generations. It exists as part of the larger architecture of the solar system, one world among 8 planets, dozens of moons, and countless smaller bodies, all held in their paths by gravity's invisible hand. The solar system itself represents a stable configuration that has persisted for 4.5 billion years and will persist for billions more. The planetary orbits, while they do change slowly over time, remain confined to predictable ranges. The Sun burns steadily, fusing hydrogen into helium, providing the energy that drives weather, climate, and atmospheric circulation on Venus, Earth, and the other planets. This entire system exists within one of the spiral arms of the Milky Way galaxy, orbiting the galactic center once every 230 million years or so, carried along with billions of other stars in the galaxy's rotation. From the perspective of the galaxy, our solar system is unremarkable, one stellar system among hundreds of billions. From the perspective of the solar system, Venus is just one planet among 8. But from our perspective as inhabitants of Earth, Venus holds special significance. It is our closest planetary neighbor for much of the time. It is the most similar planet to Earth in size and bulk composition. It is the brightest natural object in our night sky after the moon. And it is a world that challenges our understanding, that raises profound questions, and that continues to reveal new details with each new observation. As you settle into rest, consider the quiet persistence of Venus in its orbit. While you sleep, Venus continues its slow rotation, taking 243 days to complete one turn. The atmospheric winds circle the planet every 4 days, driven by processes that operate continuously whether we observe them or not. The clouds form and dissipate. The sulfuric acid droplets grow and fall and evaporate in an endless cycle. The surface remains at 737 Kelvin, day and night, poles and equator, unchanging in its constancy. There is something peaceful in contemplating these vast, ongoing processes that operate on timescales far beyond human experience. The rotation of Venus, the circulation of its atmosphere, the volcanic reshaping of its surface, all proceed according to physical laws that have governed them for eons. These processes are indifferent to human concerns, operating in their own rhythms, following patterns set by the fundamental forces of nature. The clouds at 60 kilometers altitude drift eastward at 100 meters per second, circling the entire planet in 4 days. Individual droplets form in the upper cloud layers, grow as they accumulate sulfuric acid molecules, slowly fall through the cloud deck, taking weeks to descend 40 kilometers, and finally evaporate near the cloud base, releasing their sulfur dioxide and water vapor to begin the cycle again. This cycle has operated for millions of years, perhaps billions, and will continue as long as Venus retains its atmosphere and receives energy from the sun. The volcanic surface lies beneath, recording the most recent episode of resurfacing that occurred perhaps 300 million to 600 million years ago. The lava plains extend across 90% of the planet's surface, overlapping flows creating textures visible in radar images. Impact craters dot the surface, evidence of asteroids and comets that have struck Venus over millions of years. The distribution of these craters, their pristine state of preservation, tells us that the surface is relatively young and has not been significantly modified since the last major volcanic period. Scattered across these plains, the shield volcanoes rise: Mart Mons, Sapus Mons, Oza Mons, and over 1,600 others larger than 20 kilometers across. Each volcano represents countless eruptions that built up the structure over time, layer upon layer of solidified lava. Some may still be active, quietly adding to their mass. Others may be dormant or extinct, monuments to past volcanic vigor. We cannot yet say with certainty which volcanoes are active, but future missions may provide that answer. The highland regions, Ishtar Terra, Aphrodite Terra, and others, rise above the plains, their formation mechanisms still debated. Maxwell Montes in Ishtar Terra reaches 11 kilometers above the mean radius, making it the highest mountain range on Venus. How did these mountains form without the plate tectonics that creates most mountain ranges on Earth? Did compressional forces squeeze the crust into folds and uplifts? Did mantle plumes push up the terrain from below? The answer remains uncertain, awaiting more detailed data about Venus's internal structure and geological history. Throughout the planet's interior, heat flows outward from the core. The core itself, probably consisting of iron and nickel like Earth's core, generates heat through radioactive decay of long-lived isotopes and releases primordial heat left over from Venus's formation. This heat drives mantle convection, causing rock to slowly circulate in the mantle, rising where hot, descending where cooled. The convecting mantle in turn drives volcanic activity at the surface, bringing molten rock up from below to erupt and resurface the planet. The mantle convection operates on geological timescales, with rocks moving perhaps centimeters per year at most, completing a circulation cycle over millions of years. This slow churning has continued throughout Venus's history and will continue into the distant future. Unlike Earth, where plate tectonics provides a mechanism for the mantle to interact with the surface through subduction and seafloor spreading, Venus's mantle must interact with a single, planet-wide lithospheric plate. How this interaction works, how heat escapes from the interior, and how it drives surface volcanism remain active areas of research. The lack of a magnetic field means Venus's interior differs from Earth's in at least one important way. Either Venus lacks a liquid outer core, which seems unlikely given the planet's size and composition, or the core exists, but the slow rotation prevents dynamo action. The second explanation appears more plausible. The core might be slowly convecting, and it might conduct electricity as molten iron does, but the rotation is simply too slow to organize that convection into the patterns necessary for magnetic field generation. Without a magnetic field, the solar wind interacts directly with Venus's upper atmosphere, as described earlier. This interaction creates the induced magnetosphere and contributes to atmospheric loss over geological time. The rate of loss is slow enough that it doesn't significantly deplete the massive atmosphere over millions of years, but over billions of years it can remove substantial amounts of lighter elements. The deuterium enrichment we observe resulted from billions of years of hydrogen loss, gradually removing normal hydrogen while leaving deuterium behind. This long-term evolution of Venus's atmosphere connects to the broader question of how planets change over geological time. Venus today looks nothing like Venus 4 billion years ago. The young Venus may have had liquid water on its surface, a moderate climate, and perhaps even conditions suitable for life. Over hundreds of millions of years, the greenhouse effect intensified, the water evaporated and was lost to space, carbon dioxide accumulated in the atmosphere, and the planet transitioned to its current state. Earth has also changed dramatically over its history, but in different ways. Early Earth had no oxygen in its atmosphere until photosynthetic life began producing it around 2.5 billion years ago. Earth's continents have rearranged themselves multiple times through plate tectonics, assembling into supercontinents and breaking apart in cycles lasting hundreds of millions of years. Earth's climate has varied from ice ages that froze much of the surface to warm periods where no ice existed even at the poles. Yet, throughout all these changes, Earth maintained liquid water oceans and avoided the runaway greenhouse that transformed Venus. Understanding why these two similar planets followed such different paths remains one of the central questions in planetary science. The answer informs our broader understanding of how terrestrial planets work, what makes them habitable or inhospitable, and how we should think about the countless rocky exoplanets we are discovering around other stars. Every measurement we make of Venus contributes to answering these fundamental questions. The study of Venus also connects to practical concerns about Earth's climate. The runaway greenhouse effect on Venus demonstrates what can happen when greenhouse gases accumulate in an atmosphere. While Earth is in no danger of becoming Venus-like in the foreseeable future, the basic physics of how greenhouse gases trap heat applies to both planets. Understanding these processes in detail, observing them operating on Venus, helps us refine climate models and better predict how Earth's climate will respond to changing atmospheric composition. Venus provides a natural laboratory where greenhouse warming operates at an extreme level, unmodified by complicating factors like oceans, vegetation, and ice caps. The atmosphere's response to solar heating, the circulation patterns that develop, The way heat is transported from day side to night side and from equator to poles all can be studied on Venus and compared to theoretical predictions. Discrepancies between observations and models point to gaps in our understanding that need to be addressed. Similarly, studying atmospheric chemistry on Venus helps us understand chemical processes that occur in planetary atmospheres generally. The formation of sulfuric acid clouds through photochemistry, the cycling of sulfur compounds between different oxidation states, the trace gas chemistry involving carbon monoxide, carbonyl sulfide, and other species all provide data for testing atmospheric chemistry models. These models apply to Earth's atmosphere as well, though with different compositions and conditions. The exploration of Venus thus serves multiple purposes. It satisfies our curiosity about our neighboring planet. It provides crucial data for understanding planetary evolution and habitability. It tests our theories of atmospheric physics and chemistry. It challenges our engineering capabilities and drives technological innovation. It may even, if microbial life is discovered in the clouds, transform our understanding of life's possibilities and distribution in the universe. For now, as you rest, Venus continues its journey through space, a constant presence in the inner solar system. Its orbit brings it near Earth every 584 days, allowing us to observe it as a brilliant evening or morning star. Its slow rotation turns it imperceptibly beneath its thick cloud blanket. Its atmosphere circulates in patterns we are still working to fully understand. Its surface remains largely hidden, but slowly reveals itself through radar mapping. The planet exists in a state of balance, though not equilibrium. Energy flows in from the sun and out to space, with the greenhouse effect trapping heat to maintain the high surface temperature. Chemical reactions continuously transform atmospheric constituents, with photochemistry creating sulfuric acid in the upper atmosphere while thermal chemistry breaks it down at lower altitudes. Volcanic processes may or may not be actively adding new surface material and releasing gases into the atmosphere. All these processes interact to create the Venus we observe today. This Venus will persist for billions of years into the future. The sun will slowly brighten as it ages, increasing the solar energy Venus receives. Though this change occurs over time, scales of hundreds of millions to billions of years. Eventually, perhaps 5 billion years from now, the sun will exhaust its hydrogen fuel and begin expanding into a red giant. At that point, the sun will grow large enough to potentially engulf Venus entirely, or at minimum, heat it to temperatures that will vaporize the surface and blow away the atmosphere. But that distant future remains unimaginably far ahead. For now and for eons to come, Venus will continue, much as it is, circling the sun, rotating slowly backward, maintaining its thick atmosphere and scorching surface. The regularity of its orbit, the constancy of its atmospheric processes, the persistence of its basic state all contribute to a sense of cosmic stability. While human concerns change from day to day, Venus continues unchanged on the timescales we experience. It existed long before humans evolved and will exist long after our species has vanished. Its processes operate according to physical laws that have remained constant throughout the universe's history. There is something deeply restful in contemplating these vast scales of time and space, these processes that operate far beyond human influence or concern. The clouds of Venus drift eastward at 100 meters per second, whether anyone observes them or not. The surface maintains 737 Kelvin, whether we measure it or not. The orbit continues its nearly circular path, whether we track it or not. These facts have a quality of inevitability, of natural law operating in its domain. As your thoughts slow and quiet, let your mind rest with the image of Venus following its path, a bright point of light in our sky, a whole world of extreme conditions and ongoing processes, a cosmic neighbor that shares our solar system but differs so profoundly from our home. Let the scales of time and distance that separate us from Venus create a sense of perspective, a recognition that we are part of a larger cosmos operating according to principles far grander than our daily concerns. Thank you for listening to this exploration of Venus. If you found this journey through the facts about our sister planet calming and interesting, I'd appreciate it if you would like this video and subscribe to Nebula Nights. Subscribing helps us continue creating long-form, relaxing space content that you can fall asleep to or simply enjoy at your own pace. There's always more to explore in the quiet depths of space, and I'd be honored to have you along for future journeys.